This is part 5 of a series of videos about compilers and the compilation of computer programs. By now, the front end of the compiler has scanned, parsed, and translated the source code into an intermediate representation, such as an abstract syntax tree, or relatively low-level 3-address code. All of the syntactic and static semantic errors have been detected, and there may have already been extensive optimization to the intermediate code. Finally, the back-end task of the compiler can begin, the generation of executable machine code. The primary tasks of the object code generation phase are instruction selection, deciding which machine code instructions map to which intermediate code instructions, register allocation and assignment, deciding which values to keep in which registers. This should now be much easier if the compiler is working on low-level intermediate code, such as 3-address code. And instruction ordering, deciding the order in which instructions should be executed. Again, much of this work may have already been done by optimizing basic blocks of 3-address code. Of course, many of the problems faced by the code generator are intractable. For example, there's no perfect way to allocate registers to variables. Nevertheless, heuristic techniques can still produce excellent object code. But the code generator might need to make several passes over the intermediate representation to get there. The final phase of code generation might also involve some machine-specific optimizations to take advantage of modern processor architectures. Indeed, much of the work the compiler has to do depends very much on the processor architecture. The most well-known processor architectures are RISC and CISC. As their names suggest, a reduced instruction set computer has a smaller instruction set than a complex instruction set computer. Typically, a RISC machine uses 3-address instructions, whereas a CISC machine uses 2-address instructions. For a given task, a RISC machine might need several instructions, whereas a CISC machine can perform the same task with fewer instructions. For example, a CISC machine might have a multiply instruction in its instruction set, whereas a RISC machine would perform the same job using repeated addition. This means that the executable code for a RISC machine takes up more memory. However, most RISC instructions require only one clock cycle to execute, whereas a CISC machine needs more clock cycles per instruction. Arguably then, neither of these architectures performs better than the other. The more complex chips of a CISC machine do make them a little more expensive to produce. For a given sized instruction register, the CISC machine must allocate more bits to the operation code of an instruction in order to support a larger number of instructions. This leaves fewer bits for the operand of an instruction. To get around this, the CISC machine will have more different ways to specify register and memory addresses in an instruction. That is, more addressing modes. A typical RISC machine will have about 5 simple addressing modes, whereas a typical CISC machine might have over a dozen rather more complex addressing modes. A RISC machine typically has 32 registers in the CPU, whereas a CISC machine can have as few as 8. All of this means that the back end of a compiler for a RISC machine has more work to do transforming high-level source code into machine code. Here's a simple model of a machine language. For the purposes of this discussion, commands are shown in assembly language rather than as strings of 1s and 0s. This is reasonable because one assembly language command corresponds to one machine code command. Translation from assembly code to binary machine code is a very simple business. All the hard work has already been done. Also, for the purposes of this discussion, we can see variable and register names here. In reality, there are no symbolic names in machine code. Each variable is known by its memory address and its size, albeit a logical address which is ultimately managed by the operating system and the target machine. Again, it's reasonable to show these names here because a machine code generator can easily calculate machine addresses from offsets and other information stored in the symbol table. Most machine language commands begin with an operation code, and that's usually followed by 1, 2, or 3 operands. A halt instruction is an exception. It needs no operands at all. Generally speaking, some or all of the operands of a machine code operation need to be in registers. These are examples of load instructions. The first copies the contents of memory location X into register R1, and the second copies the contents of register R2 into R1. The destination field is usually written before the source field. This is an example of a store instruction. It copies the contents of register R1 into memory location X. Again, you can see that the destination field is written first. Instructions that perform calculations include add, subtract, and increment commands. The add instruction here adds the contents of registers R2 and R3 together and places the result into register R1. The subtract instruction takes the value in register R2, subtracts the value in register R3 and puts the result into register R1. The increment instruction adds 1 to memory location X and puts the result back into X. In assembly code, a jump command, that is a branching command, can pass control to a label or to a line number. In this example, control is passed to a label called end. In machine code, jumps are actually made to instruction addresses. For readability, we'll stick with labels in this discussion. An unconditional jump has only one operand, but a conditional jump has two, in this model language anyway. Typical conditional jumps include branch if less than 0 and branch if greater than 0. The first example here will jump to a label called end if the contents of register R1 are less than 0. The second will jump to line 300 if the contents of R1 are greater than 0. This instruction set looks very limited at first sight, but it's surprising just how much can be achieved with only a handful of possible operations. It also illustrates just how problematic it is for a compiler to select the best combination of low-level instructions when translating a high-level program. A simple approach to instruction selection would be to deal with one basic block at a time, examining each 3-address code instruction in turn and replacing it with a sequence of appropriate machine language statements. If the intermediate code is already optimized, this might well produce adequate code. For example, for the 3-address instruction x equals y plus z, the compiler might simply select 3 machine code instructions. Load the contents of memory location y into register R1, add the contents of memory location z to the contents of R1 and put the result back into R1, then store the contents of R1 back into memory location x. However, this approach will generate a lot of redundant loads and stores. Here we have 2 3-address instructions in which the second relies on the value of x calculated by the first. This is the machine code generated by dealing with each instruction in turn. This instruction is unnecessary because register R1 already contains the value of x. In fact, if x isn't going to be used again, this instruction is also redundant. A simplistic approach can easily lead to unacceptably inefficient machine code. A better approach to instruction selection would be to use a data structure that keeps track of which program variables currently have their values in which registers, to avoid unnecessary loads and stores. A register descriptor can be used to hold the name of the variable whose value is currently stored in that register. An address descriptor can also be used to track the location or locations of the most up-to-date value of the variable. The obvious place to store this information is in the symbol table, which already contains an assortment of information about each name. So now consider this example of a basic block. A, B, C and D are variables whose values are stored in memory and presumably are still available when the block ends, that is, they are live on exit. T, U and V are temporary variables that are only used within the block. The register descriptors are all empty when translation of the block begins, and the address descriptors indicate that the contents of the variables A, B, C and D are in memory and up to date. The first 3-address instruction does 2 loads. making use of registers R1 and R2. The value of variable b is not used again within the basic block, so the result of the first subtraction operation, t, is put into register R2. The most up-to-date value of b is still in memory. This is what the register and address descriptors look like now. The register descriptors for R1 and R2 indicate their contents, and the address descriptors show the current locations of the values of the variables. The machine code for the second 3 address instruction loads C into R3, but it does not need to load the value of A into a register because it's already in R1. And since the value of A isn't used in the block again, the contents of R1 can be overwritten with the value of U that's produced by the calculation. So this is how the register and address descriptors look now. The address descriptor for A has been changed to indicate that its value is no longer in R1. Both of the values needed for the third 3 address instruction are now in registers, so the add operation requires no loads at all. Because C won't be used again within the block, and C has a value in memory, it need not be kept in a register. So the result of this calculation, V, can go straight into R3. This is what the register and address descriptors look like now. Assigning the value of variable D to variable A requires that D be loaded from memory into a register. The value of temporary variable T, which is in R2, can be overwritten because T isn't used again within the block. Since this was essentially a copy operation, the register descriptor for R2 is updated to indicate that it contains the most up-to-date value of both D and A. The value of A in memory is now out of date, so the address descriptor for A is adjusted to indicate the fact. The values needed for the final add operation are both in registers. Since the value in temporary variable U will not be needed again, the new value of D can go into R1. The register and address descriptors are updated to indicate that the latest value of D is now in R1 only. In fact, at this stage, we can see that the most up-to-date value of A is also in a register. When the block finally exits, the most up-to-date value of any non-temporary variables that are live on exit need to be stored back in memory. The address descriptors for A and D indicate that they need to be stored. And this is the final picture, at least when the machine code for this basic block has been dealt with. Generating good machine code for a CISC machine is problematic. Converting one 3-address instruction at a time into machine code is unlikely to take full advantage of the rich instruction set and the variety of addressing modes. A single CISC machine code instruction might be able to do the same job as several intermediate code instructions. Tree rewriting is an alternative way to select instruction sequences of machine code instructions to match an intermediate representation of a program. The code generator employs a set of tree rewriting rules that describe the instruction set of the target machine. These rules are collectively known as a tree translation scheme. Each rule is represented by a simple tree template, along with a replacement node. And each rule also corresponds to a single machine code instruction. The input of the code generator is a sequence of abstract syntax trees representing the original program. These input trees may have been built from previously optimized intermediate code. The code generator traverses the input tree looking for subtrees that match the rules, replacing them with single nodes and emitting machine code instructions as it goes. Once the input tree has been reduced to a single node, the process is complete. Here are some tree rewriting rules from a tree translation scheme. This is the rule for the add instruction. The tree template indicates that the contents of one register, denoted Ri, is added to the contents of another, Rj, and that the result is placed into the first of the 2 registers, Ri. The replacement node in this case is Ri. If the input tree is found to contain a subtree with the same operator and the same children, then the subtree will be converted into the single replacement node specified in the rule, and the corresponding machine instruction will be emitted. The load from memory instruction is represented by the simplest of tree templates, consisting of only one node, mx, with no children at all. mx represents a variable located in memory, and the replacement node is a register. If a memory-based variable is identified in the input tree, it'll be replaced with a register, and the corresponding load instruction will be omitted. The rule for loading a constant is very similar. CA represents a constant value, such as a number, and the replacement node is a register. The store instruction is essentially a copy operation in which the contents of a memory location are made equal to the contents of a register. Let's see how these rules can be applied to an input tree. Suppose we have an input tree for the expression x equals x plus 1. A traversal reveals the first matching rule. The rule specifies that node x should be replaced with a register. So the node for x in the input tree is replaced with a node for register R1, and an instruction to load x from memory into register R1 is omitted. The next matching rule is that for loading a constant into a register. Another input tree node is replaced, and the instruction to load the value 1 into R2 is omitted. Now the rule for the add operation is identified as a subtree of the input tree. There's an addition operator node with 2 registers as its children. The subtree is replaced according to the rule, and an add instruction is generated. The successive replacement of subtrees with replacement nodes is known as tree tiling. Finally, the rule for a memory store can be tiled onto the tree. The replacement node is applied, and the store instruction is omitted. Once the input tree has been reduced to a single node, the process is complete for this input tree. The real power of the tree rewriting approach to instruction selection lies in the fact that it might be possible to tile a given input tree in a number of different ways. This means that there's more than one possible combination of machine code instructions that could be generated. One way to achieve a sequence of machine code instructions is to apply the maximal munch approach to tiling the input tree. Starting at the root of the tree, the code generator will look for the biggest possible tile that matches one of the rules and emit the instruction. It will then work its way down, always looking for the biggest possible tiles and emitting instructions as it goes. Since each tile represents one machine code instruction, this approach is likely to find the minimum number of instructions needed to match the input tree. In a RISC machine, where many of the instructions require only one clock cycle each to execute, this will probably result in good code. However, the greedy maximal munch approach is not necessarily the best, particularly with a CISC machine, in which a single instruction can take several clock cycles to execute. Each tree rewriting rule and its corresponding machine code instruction has an associated cost in terms of the time the processor takes to execute it. What the compiler really needs to find is the sequence of machine code instructions with the lowest total cost. In this example, the code generator tiled the input tree 4 times and generated 4 machine code instructions to increment the value of x. But some processors include an increment instruction. So in this case, the compiler would have a single rule that lets it tile all of these nodes in one go. The increment instruction may well require several clock cycles to execute, but the assumption when it comes to CISC is that the overall processing cost of a single instruction is probably lower than otherwise. The objective of the code generator then is to select the lowest cost instructions possible when traversing the input tree. This might be achieved in a number of different ways, perhaps by first linearizing the input tree and then applying string pattern matching algorithms. Dynamic programming is another technique often employed to solve this kind of intractable problem, but that's another story. Once the machine code has been generated, it may undergo further optimization. Peephole optimization is a common technique used by code generators. This involves examining a few lines at a time through a small sliding window and matching these against a pattern library of more efficient instruction sequences that have the same effect. Indeed, peephole optimization may have already been applied to the intermediate code. from which the machine code was derived. Of course, peephole optimisation is easier said than done. Several passes may be required to produce the best possible object code, and there may be a number of special cases that need to be handled in special ways. Some of the things that peephole optimisation might do is to remove redundant identifiers, evaluate constants, remove unreachable sections of code, identify common sub-expressions, unfolding loops, and eliminating whole procedures. To summarise, object code generation is perhaps the most complex stage of compilation. It depends very much on the machine architecture because this dictates the size and complexity of the instruction set and the number of memory addressing modes and CPU registers available. Object code generation is relatively straightforward for reduced instruction set computers, particularly if there's already a good low-level intermediate representation to work with, but it's considerably more involved for complex instruction set computers. One of the main tasks of the back end of the compiler includes machine code instruction selection. This may be done by simply substituting each line of the intermediate code with a corresponding sequence of machine code instructions. Alternatively, more efficient code may come from matching tree rewriting rules to sections of abstract syntax trees. Instruction selection based on the processing cost of machine instructions will often produce efficient code. Register allocation and assignment can be done by means of register descriptors and address descriptors. And finally, optimization techniques such as peephole optimization can be applied to the object code.